Urine formation deals with something called the glomerular filtration rate, or the GFR. Okay? What a GFR is the number of milliliters of fluid flowing through Bowman's capsule. So again, very simplistic view of a nephron. And you have this. And what we're talking about is the GFR, the glomerular filtration rate, is how fast is the fluid getting into the nephron. That's basically what the glomerular filtration rate is. Okay? A number of milliliters flowing through Bowman's capsule per minute. We deal with something called renal clearance. Renal clearance is a volume of plasma that's rendered free of a state of material in 1 minute. How fast is that material, whatever it is, substance X we'll call it, can get from here over to here into the nephron? How do we clear it? So what is a GFR? We could find this GFR if we could get some sort of magic substance that is filtered in here, and it's not, none of it will actually get reabsorbed, and none of it will be secreted. So 100% of it comes in here, 100% of it will go out in the urine. That's how you have to find it. Because if you have something that's going to be subtracted here and things going to be added, then you're not going to find an accurate thing. Does that make sense? You got to know exactly 100% that's being filtered, and 100% of that, not 110%, not 98%, but 100% of that is going to go out in your urine. So we got to find this magic substance. But as you see, with sodium comes in here. Some of it's going to be reabsorbed, some will be excreted. You can't do potassium because some of it's going to be reabsorbed, some of it's going to be, you can't use hydrogen. Some of it's going to go this way, that way. Even glucose, it's 100% goes this way. So we can't use any of that stuff. We have to be able to find out with the GFR by using this magic substance. So in order to do this, before we find this magic substance, there's a formula here that you should be able to use. The amount of the filtrate, or the infiltrate, same thing, all right? The amount of this substance X in the filtrate has to equal the amount that's in the urine. Again, if 100% comes in here, 100% goes out of your urine. So it has to be equal. So what we have to do is plug in a few things. The amount of this substance, we'll say P is the amount, and here's the X, whatever that substance is, times the rate. The rate that it passes right through here. You guys are driving on the highway, you're driving 60 miles per hour. Well, that's what I'm saying here. Let's say the rate is 60 miles per hour. The rate, okay? That should equal the amount of that substance in the urine, and the V stands for the rate of urine. These are numbers that we've already, they're arbitrary letters. These letters over here, P and V, that's what they use in all the medical books and stuff. So we might as well use the same things. So we could reverse this through algebra. So we could have, let's say, UV, and then we divide it by the P over here. Does that make sense? How to get this? So we want to solve for GFR. If we know this amount, and we know the rate of urine by just how often you pee, and we could collect that in a bag if we want to see how fast it's going, then we can figure out what the GFR is by just solving for GFR. Just basic algebra. Okay? So we do have this magic substance. It's called inulin. It is not insulin. It is far from it. It's totally different. That's where spelling counts on this thing, right? Inulin, not insulin. It's totally different. Inulin is this synthetic artificial substance that man has created, and they can inject it in the person. And this inulin can go right from here into here, and 100% will go into the nephron, and 100% will go out in the urine. So we can actually figure out a GFR if we inject and follow this inulin. The problem is, doing that to every patient is kind of a tedious thing. We don't want to keep on injecting. We want to know the function of the kidney. We're not going to inject that in everybody. That's just too tedious to do that. So we have another way that we can do this. And I'll show you where we would need to inject that in certain people, if they need to see what the function of that kidney is in that person. But there's an easier way we could do this too, to estimate the GFR. Like I said, it's very tedious to be injecting that into everybody's arm. We could use creatinine. Creatinine is a byproduct of muscle metabolism that all humans have. It just comes out. Now in dogs, it's neither reabsorbed nor secreted. So in dogs, it's perfect. Creatinine comes into here, 100% it comes into here, and 100% will actually go out here. Perfect for dogs, but we're not dogs. In humans, it's not reabsorbed, but very little does get secreted. So it's not going to be the best, but it's pretty darn close. But however, when creatinine is measured with other substances, this error is fixed. In other words, how I said that creatinine is not reabsorbed in a human but secreted very little, it kind of cancels that secretion because other substances are measured with it. And I don't want to get into the details about that, so it kind of eliminates that. Okay? Let me just explain to you that there is this last way, this is probably another way to estimate a GFR, and this is the easiest way. But you should know the evolution of how this came about, because there's going to be times you're going to have to use the old-fashioned way to do that, and I'll show you with the inulin. So let me just show you the easiest way, and this is the one that they use often, most common thing they use. It's the amount of creatinine that's in your bloodstream. If creatinine in the blood is constant, since muscle mass is constant, then we could say that we could control that. In other words, the amount of, look what's happening here. If there's good flow of creatinine going through here, you're going pretty fast. That's good. That's telling us that the kidney is working properly. That creatinine is going this way. In other words, the creatinine is not staying in the bloodstream. Does that make sense? If there was some kind of disease, and let's say the kidney is not functioning right, then the creatinine is not going to be able to get into the nephron, which means the creatinine is going to stay in the bloodstream, which means that the plasma creatinine is going to increase. Does that make sense? It's the same thing as you driving 60 miles per hour on the highway, and to get from point A to point B, you get them in timely fashion. You could say that without even asking, there was no traffic. You got here pretty fast. You see what I'm saying? But if there's a motor vehicle accident that happened on there, now you're not going to be driving 60 miles per hour, but you might be driving 20 miles per hour. And the cars are going to accumulate prior to the motor vehicle accident. And there's going to be a lot of cars at that place, and there's not going to be much cars going past that motor vehicle accident. So that's saying that if there's going to be more cars on the highway prior to that motor vehicle accident, then something's going on in that highway. If there's going to be more creatinine in the bloodstream, then you could say that there's something going on at the nephron level because it's not being pushed into here. Is that clear about that? So So if you think about this, if there's some sort of decrease in GFR, right? If there's going to be a slower rate of this going through here, then there's going to be a lot more creatinine up here. Does that make sense? It should. So if a person has a lot of creatinine in their blood, I could say that they have something wrong with their GFR, which means they have some form of kidney disease. Okay? So if you see an increase in creatinine in the blood, suspect some sort of kidney disease. If there's going to be more cars on the highway, expect that there was probably a motor vehicle accident. Right? It makes sense. And the rate will be very slow. There'll be less fluid getting into the nephron. Okay? So these are the three exceptions that we can't use for the method. These are the people that have a continuous amount of muscle mass that changes. So you can't use creatinine. This is only good if creatinine is going to be fairly the same year to year. People who are newborns, because their muscle mass every year is growing and growing and growing. Bodybuilders, Arnold Schwarzenegger, they're building more muscle mass, so they're going to produce a lot more creatinine. That's not going to be a good judge, to judge to see what their kidneys are doing. Or any kind of muscle wasting disease, muscular dystrophy, that kind of stuff. Then yeah, they're going to be losing muscle mass at a rapid rate. It's not going to be good over here. So these three people, yes, they will need some kind. You've got to check what their kidney function is. They have to get the inulin injected because you can't utilize creatinine. Is that clear about that? Okay. All right. So glomerular filtration rate. If you understand this, if it starts building up inside the bloodstream, then there's some kind of motor vehicle happening or accident happening in the kidney. There's some sort of kidney disease. Now, basically, if the GFR is greater than 60 milliliters per minute, there's nothing really happening. It's either nothing's really happening, no kidney disease, or very early onset of kidney disease where you're really not going to see it so early. What's nice about the kidney, it's a very residual organ. You don't really get end-stage kidney disease until 80% of your kidney starts deteriorating. So they're pretty good. Yeah, what I'm saying is 80% of the kidneys have to be malfunctioning for you to really start seeing a lot of symptoms, for you to actually see end-stage renal disease. That's when you should start considering, renal transplants. All right? You don't have to worry about 25%. You still have good kidney function with 25% bad. But that's why the creatinine will be able to pick up on these things quite early. Okay? So you don't have to worry about the numbers here. Just understand that GFR greater than 60 milliliters per minute, that means things are going smooth. But anything less than that, kidney disease. So the higher the plasma creatinine is, the more of the kidney disease that you have. Does that make sense? We look at the creatinine levels in the blood, and it should be at a certain level. Okay? In urine formation, it's about 1 cc or 1 milliliter. Cc and a milliliter is the same thing. So 1 cc per minute per kilogram. So if you have a 70 kilogram man, which is about 144 pounds, you should be able to put out, if it's 70 kilograms, it's about 70 milliliters of urine per hour. Okay? And you should know those things, right? When you get into these other fields, you should know about these things. Okay, so that's all I want to say about GFR. There's a good video that I'm going to put on right about here. And I want you to watch that. It also incorporates not just GFR, but it also incorporates hydrostatic pressure, and osmotic pressure when dealing with the Bowman's capsule. And we did all those calculations. So do take a look at that. It's a nice review. It's about 6 or 7 minutes.
Hiya, welcome to Biomed Sessions with me, Ruse. Today we're going to be discussing glomerular filtration. Here we have our renal corpuscle, which is a structure essential for the filtration of blood in the nephrons of the kidney. One part of the renal corpuscle is the glomerulus, which is basically a network of capillaries. The other part is the surrounding Bowman's catchwall. Most capillaries have an arterial end and a venous end. This is not the case here, as blood flows through the glomerulus from the afferent arteriole to the efferent arteriole, and as this occurs, components of the blood are filtered out. The fluid that enters the catchwall is called glomerular filtrate, and filtration occurs across an ultrafiltration barrier. A good analogy for the ultrafiltration barrier is a kitchen strainer. Now if you pour a nice herby broth of vegetables into the strainer, you will see that large vegetables are left behind, whereas water and anything else that dissolves in it, plus tiny particles, are able to pass through. Now with our glomerulus, molecules less than 1.8 nanometers are freely filtered out, whereas molecules more than 3.6 nanometers are not filtered. Let's take a look at a zoomed in section of the ultrafiltration barrier. As you can see, there are 3 layers. Our bottom layer is the endothelium of the capillary, which contains these pores known as fenestrations. This layer basically lets everything through except for blood cells. Our middle layer is the basement membrane, which prevents the filtration of large proteins. And our outer layer consists of podocytes, part of the Bowman's catchwall. These look like monsters wrapping their arms around the layers below, and they themselves have many finger-like projections called pedicels, which are so close to each other that there are just narrow filtration slits between them, which allow only small molecules to pass through. One thing to note is that the ultrafiltration barrier is charge selective. As all 3 layers contain negatively charged glycoproteins, it is difficult for negative molecules to pass through. Hence, serum albumin is not filtered, despite being in the size range. Ultrafiltration of blood to form glomerular filtrate depends on a balance between the forces that favour filtration and those that oppose it. In general, we can refer to these forces as Starling forces. In order to fully understand glomerular filtration, you need to know about hydrostatic and oncotic pressure, so I'm going to give you a very simplified explanation. Hydrostatic pressure refers to the force a fluid exerts on the walls of its compartment. This would be either the walls of the capillaries or the Bowman's catchwall. I like to think of it as pushing, because it is kind of like the way water pushes on the inside of a water balloon as it's being filled up, but in this instance the fluid can be pushed out. Oncotic pressure is pressure exerted by plasma proteins on the walls of the compartment in which they are contained. It kind of has a sponge-like effect, encouraging fluid to be drawn in, therefore I like to think of oncotic pressure as pulling. The major driving force for filtration is the hydrostatic pressure of the glomerulus, which forces fluid out of the capillary. This is opposed by hydrostatic pressure of the Bowman's catchwall and the oncotic pressure of glomerular capillary protein. Note, we tend to ignore oncotic pressure of the Bowman's catchwall as only tiny amounts of protein are usually present in the glomerular filtrate. Our net filtration pressure, NFP, equals to the pressures favouring filtration minus the pressures opposing filtration, i.e. hydrostatic pressure of the glomerulus minus hydrostatic pressure of the Bowman's catchwall minus oncotic pressure of the glomerular capillary protein, which is equal to 10 millimeters of mercury. There are many nephrons, and hence there are many renal corpuscles in each kidney. Glomerular filtration rate, GFR for short, is the total amount of filtrate formed by all the renal corpuscles in both kidneys per minute. It can be used as a clue to assess whether an individual has kidney impairment. GFR not only takes into account NFP, but also surface area available for filtration and permeability of glomeruli. In fact, GFR equals to the product of surface area and permeability multiplied by NFP, which can be condensed to the filtration coefficient multiplied by NFP. The permeability and surface area of glomerular capillaries tend to be greater compared to other capillaries due to the fenestrations and extensive branching and looping. Hence the filtration coefficient is high, and so there is a high degree of filtration in the glomerulus. It is important to note that when considering GFR, we must also take into account the number of functioning nephrons and how effectively the glomeruli filter blood. So, how can GFR be changed? Well, of course, by altering either the filtration coefficient or NFP. For example, if we constrict the afferent arteriole, the hydrostatic pressure of the glomerular blood will decrease due to the reduction of blood available for filtration. As this pressure is associated with NFP, this will also decrease, and hence GFR will decrease. In a later video, we'll go into more detail about the control of GFR and how it is estimated. But for now, I would like you to understand that the glomerulus, alongside the Bowman's capsule, is highly specialized in the filtration of blood. And glomerular filtration rate, GFR, is a good indicator of how well the kidneys are working. So, if this tutorial was helpful to you, show it by liking the video, and if you would like to see more tutorials from me, do subscribe. Okay, see you in another video. Bye!
A quick recap, you should know all about this and all the different parts of the nephron. We've dealt with this a few times already. You should know in terms of the area with the loop of Henle, where sodium potassium chloride is not going to be able to get absorbed or reabsorbed, and water, it doesn't get reabsorbed in this part of the loop of Henle, right? It gets more concentrated down here. This is where aldosterone targets mostly. Here's where ADH targets mostly. Okay? You should be able to put that all together. You can do this on your own too. This is going from the renal arteries to the nephron to the calyx, all the way out when you pass urine. When you get to the nephron, here's the different parts. You can look at this, it's pretty straightforward. Okay? And same thing here when you take the nephron and the blood vessels together. All right? Very busy slide. Again, the video that I found was puts this in perspective. Remember how this is the loop of Henle going this way, and then the blood goes this way. So you got countercurrent exchanger between the descending loop of the loop of Henle and the blood vessel here, vasa recta. But then we also have the countercurrent multiplier when we're dealing with these two over here. And those two videos that I incorporated in the other videos earlier should shed a lot of light to those things. Okay?